Hello and welcome. We are on page 69 talking about our precipitation reactions. So remember from our types of reaction videos, a precipitation reaction is always going to be a double replacement reaction where two aqueous solutions have formed an insoluble product. That insoluble product or solid is called a precipitate. So we do want to make sure that we are connecting all of these words. A precipitate is a solid, which is an insoluble compound. It is not going to be dissolved in water. Well, first off, let's quickly review what exactly solubility looks like with our ionic compounds. Whenever we mix a solute with a solvent, so remember solute is what gets dissolved, solvent is what does dissolving, there's attractive forces happening between the ions of our ionic compound and the dipoles of water. If that attraction, if that new ion dipole IMF is strong enough, that is what's going to allow the solute to dissolve. As it dissolves, ions separate or ionize from one another. We call that process dissociation. So we can see that down in our picture here. We have a KF solution. Each of our ions of K and F, so that's what's in the middle here, have been separated from each other. So it's actually individual K plus and F minus ions separated, floating around in there. And they get surrounded by the water molecules. When the attraction between the ion, which is in the middle here, to the dipole of water is strong enough, things are going to dissolve. Remember, water is a polar substance. It has a dipole, meaning that it has a partially positive end where our hydrogens are and our partially negative end when our oxygens are. So we can see around our positive potassium ion here, it's all the negative ends of water that are surrounding it. That's the ion dipole attraction. So the attraction between the ion of our ionic compound and the dipole of water. We can see the same thing with our negative fluorine ion here, but it's attracted to the partial positive side of the water dipole there. Again, that ion dipole force is shown with sodium and chlorine. Opposite charges are going to be attracting between that ion and that dipole. Each individual ion within an ionic compound is going to be splitting up. So the number of ions in that solution depend on the ratio in the original formula. So for example, if we have lead to nitrate, it's going to dissociate to form several different ions here. We have one lead and two nitrates. So whenever this formula unit dissociates, if one of them dissociates, it's going to form a total of 3 ions, the one lead ion and the 2 nitrate ions. Each of those ions would be individually floating around in that water, surrounded by the water dipoles of the opposite charge. So now that we've talked about what exactly it means to dissolve, let's get back to our precipitation reaction with our insoluble product. Whenever we mix these two aqueous solutions here, potassium iodide and lead nitrate, they're both going to be soluble in water. So they've dissociated into their ions. K and I are separated. Our lead and our 2 nitrates are separated. However, when we mix them together, that double replacement is going to happen there. So we see here in the instant that the solutions come into contact, all 4 ions are present. All 4 ions are separated, ionized, but as the reaction occurs, we're going to form that insoluble lead iodide. That is what's precipitating on the bottom here. So we see our lead iodide is our solid that we formed. However, the other product of this reaction, potassium nitrate, is soluble. So those potassium nitrate ions are still dissociated in water. They're still experiencing that ion-water dipole there. When looking at a double replacement reaction, we kind of need to be able to figure out what our precipitation is. Sometimes that information might be given to you. Otherwise, there are rules to determine which ions are soluble in water. There used to be a very, very long list you needed to know all the rules from, but with the new AP test, you only need to know a few basic solubility rules. The big one you need to know, which is all nice and bolded here, is number 1, what is always soluble. Alkali metal cations, which are our group 1 metals, are always going to be soluble. Anytime you have one of these group 1 metals in a compound, that compound is soluble no matter what. Same thing for ammonia. Anytime a compound contains ammonia, it will dissolve in water. And anytime it contains nitrate, it will dissolve in water. So that rule right there, those bold things that are always soluble, you must know. Generally, any other information that you need would be given to you in some form or fashion to figure out what your precipitate is. The rest of these solubility rules might be helpful to be familiar with. So there's a few other things that are always soluble. Your halogens, bromine, chlorine, and iodine are generally soluble unless they are combined with silver, lead, or mercury. Sulfate is generally soluble as well, unless it is combined with one of these metals that you see here. Your insoluble ions tend to be hydroxide and sulfide, except for when they're with those things that are always soluble from number 1, and calcium, strontium, or barium. Carbonate, phosphate, sulfite, and chromate also tend to be insoluble, again, unless they're with things from rule 1, those alkali metals, ammonia, or nitrate. So let's look at different ways we can represent a precipitation reaction now that we know how to figure out who our precipitate is, looking at those solubility rules. But before we get there, just because we mix two aqueous solutions doesn't mean there's actually going to be a reaction that happens. If we mix two aqueous solutions and we end up making two aqueous solutions, nothing actually changed. So let's check that out. Looking at this first reaction here, we have rubidium chloride and sodium bromide. They react to form rubidium bromide and sodium chloride, which are also both aqueous. Well, if they're aqueous, if they're soluble, that means that they've dissociated into their ions, and those ions are just floating around separately in water. So before and after the reaction, we still have the same 4 ions floating around in water. There actually was not a reaction that happened there. In our second reaction, we had our 2 aqueous ionic compounds that are mixed, and we formed a solid. So this, yes, indeed, is a precipitation reaction because a solid was produced from 2 aqueous reactants. When we look at the third reaction here, we have an aqueous reactant and a solid, and we're making a solid, but that is not precipitation. We are not starting from 2 aqueous reactions. So by definition, that precipitation reaction, we're starting from 2 aqueous and forming a solid. Okay, so now let's look at our ways to represent it. First way we can represent a precipitation reaction is the complete ionic equation. So starting from the full normal balanced molecular equation, we would split up any aqueous substances into their ions. So we're essentially representing it as it would be in that solution. Because aqueous substances dissociate or ionize in solution, we're going to show them split up into those ions. But things that are non-aqueous are going to stay together. Just like solid, liquids, and gases do not ionize. Only aqueous things are going to ionize. We can also show the net ionic equation. The net ionic equation is based off of our complete ionic equation, but we remove any spectator ions. Spectator ions are ions that were found exactly the same form on both sides of the equation. They did not actually participate in that reaction, so we're going to go ahead and remove them. They were just floating around in water before the reaction, and they're just floating around in water after the reaction. So here we have an example of a precipitation reaction here and the different forms that we can represent it in. In this reaction, we have silver nitrate, which is aqueous, combining with our aqueous calcium chloride. We form solid silver chloride and aqueous calcium nitrate. So in the complete ionic equation, we are going to split up any aqueous substances and leave non-aqueous substances intact. So we're splitting up our silver nitrate into its ions, our calcium chloride, and our calcium nitrate. Our silver chloride, our non-aqueous substance, is going to stay intact. So we separate those out. We do want to be counting our ions as well. So we have 2 silver ions, 2 nitrate ions, 1 calcium, 2 chlorides. Our 2 AgCl solids stays together. We have 1 calcium on the product side and 2 nitrates. So when you split it up into that complete ionic equation, it should still remain balanced. Once we have the complete ionic equation, to get to the net ionic, we want to remove those spectator ions. Spectator ions are things that appear exactly the same on both sides. In this case, that's going to be our calcium ion, so we have Ca2 plus aqueous on both sides, and our 2 aqueous nitrate ions, which we see are the same on both sides as well. So those are going to cancel out, and what remains is the net ionic equation. Only thing we do need to do with that net ionic equation is simplify our coefficients down. So our final net ionic equation would be our aqueous silver ions reacting with our aqueous chloride ions to form the silver chloride solid. Again, we just reduce those 2, 2, 2 coefficients down to 1, 1, 1. So let's get some more practice with writing net ionic equations. Go ahead and take a couple moments and try out these next couple examples. Resume the video when you're ready to check. So looking at number 1, precipitation reactions are always going to be best represented by that net ionic equation because we're only showing what is actually happening. It only shows the formation of the precipitation reaction while we're leaving out all those spectator ions which don't even participate, they don't have any change. So we are only showing that net change in a net ionic. When looking at number 2, we wanted to complete and balance the following reaction and then write the complete and net ionic equations. 2 products will be sodium sulfate and water. So when we split those up, H went with OH to form water, sodium went with sulfate to form Na2SO4. Don't forget to be crisscrossing for those new products. Group 1 metals are always aqueous and water is a pure liquid. Then we need to balance this. We have a couple 2 coefficients added in. To get to the complete ionic, we are splitting up any aqueous and keeping any solid, liquid, gas together. So once we have those all split up, remember we're counting our ions, so make sure you have the correct coefficients on those ions. All of our ions should be aqueous, and the only non-aqueous thing was our liquid water, so that needed to stay intact. Once we have our complete ionic, we can go to the net ionic by canceling out our spectator ions, those ions that are the same on both sides. Once we've canceled those out, we're left with our 2 aqueous H plus ions, our 2 aqueous hydroxides forming 2 waters, but we also need to simplify our coefficients down. Leaves our final net ionic, H plus OH minus yields our liquid water. Make sure you're keeping states of matter in those as well. Got 2 more for you to try out. Resume the video whenever you are ready to check. Whenever you are only asked to write the net ionic without that complete ionic step, the easiest way is to identify that non-aqueous substance on our product side that's going to stay together. So in part A here, that's our silver sulfate solid. So that would be our only reactant. Then we can, only product. Then we can just build in our aqueous reactants that we would need. We need our 2 silver ions and our 1 sulfate ion, which were both aqueous on the reactant side. Since our ammonium and nitrate are aqueous on the product side, they were our spectator ions as well. So there's our net ionic there. Similarly on B, we can find that liquid that's staying together. So our liquid water is made from the ions H plus and OH minus. The lithium and the sulfate were our spectator ions. So there is that net ionic equation. So that sums up our precipitation reactions and ways we should be able to represent them. So you'll need to be able to write complete and net ionic equations for any precipitation reaction.